Thank you for joining us today for a webcast on the subject of new tools to prevent centrifugal compressor surge, presented by Beta Machinery Analysis and Turbo Machinery International. The subject of surge control is one that has been coming up repeatedly in events such as the Turbo Expo and Turbo Symposium, as well as in several magazine articles published in Turbo Machinery International in recent times. So we're anticipating a lively discussion. And now our speakers. Jordan Grove is a mechanical engineer with 13 years of design, field, and monitoring experience with compressors, pumps, piping, and other production machinery. He currently leads Beta's Vibration Integrity Group in addressing plant-wide vibration risk in piping and machinery systems. He recently wrote a paper on dynamic surge analysis for the Asia Turbo Machinery and Pump Symposium in Singapore. Second speaker is Mary Beth McBain. She's a lead mechanical research engineer at Beta Machinery. She has 15 years of experience in compressor surge, rotating machinery design, failure analysis, piping dynamics, compressor development, and pulsation analysis. She has delivered various conference papers, including an application guideline on surge control at the Gas Machinery Conference. So let's welcome Jordan.
Well, thanks. Welcome, everyone, for coming. Thank you for joining us today. And as was mentioned, feel free to type in questions as we go through the presentation, and we'll look to address those at the end of the presentation. So today we're going to go through the surge control fundamentals briefly, common surge control design questions that are common within the industry, new techniques available to the industry that we're introducing today. We're going to outline a few case examples, one interaction study, and another with placement of a check valve, which I think you'll find interesting, and details of level 1 and level 2, level 3 analysis, what to use, what and when. And also we'll finish off by summarizing and getting into the questions. So I think let's get into it. So we'll just start off with a definition of surge and the purpose of surge control. So I think most of us understand on the line. We won't get into too many details today. We only have 1 hour. But surge essentially is when the compressor loses its ability to maintain positive head, or it loses the stability within the system. So that means what happens is you're having positive flow through your impeller, and surge is when the high pressure gas on the discharge side goes reverse through the impeller, even though it's still spinning in the forward flow direction. It's when the gas pressure takes over that rotational energy. When you get the flow reversal is due to a dramatic change or flow stability across the surge line. And really the surge control system involves a recycle valve, and that recycle valve is there to restore positive flow to the suction side of the compressor and depressurize the discharge system, especially in an emergency shutdown event or ESD event. The surge control system is also there to control low flow periods during process operations and help with the startup of the compressor by gradually closing the recycle loop as the compressor and the process comes online. So those are kind of a really basic, quick overview of surge and the surge control system. If we look at the plot that we have here, we can see, you can imagine your compressor. This is your wheel map. We've got our flow along the x-axis here. We've got our pressure ratio, or head on the y-axis. You can imagine, a compressor operating at this speed. We've got the different speed lines here. You can imagine it running at 100% speed, and the surge really is what happens when the flow decreases and the head increases to the point where we have this instability in the system, and we go into even full reverse flow through the impellers. You can see here is the zero flow line, and everything to the left of that line would be reverse flow through the compressor, which is something we never want. Carrying on here, we want to show you a video here to kind of give you a real example of surge from some automobile turbochargers. Now, when we load this video, it'll take a couple seconds, but you should hear, you can listen closely to the engines as it winds up, and you can actually hear the turbo, kind of a high-pitched whine on top. There's two cases, and listen to when the turbo surges. So I think I think most of you could probably hear. Hopefully, imagine there's some of you in the crowd that have some souped-up vehicles that might have some high performance turbos on there. But you can really hear, when that reverse flow happened, it makes a big bang, and in that first section of the video, you can really see how it shakes the compressor and can be damaging to it. So it's kind of a real life example of surge. So we can carry on here. Just wanted to talk a bit about some surge control system requirements. What is the primary, the primary reason to have a surge control system? And basically, it's protection. And the surge control system its purpose is to act to restore the positive flow to the compressor in an adequate amount of time. So we want to restore that positive flow before it gets negative. Secondary requirement for good operation is the surge control system shouldn't overly limit operations of the compressor. So, you don't want to be overly conservative. You don't want to have a surge control line that takes over your wheel map and limits the amount of flow flexibility you have in your compressor. We want it to provide controllability for startup and low flow periods as well. We want to avoid causing other units to surge in a multi-unit station. So we don't want our surge control system of one unit interfering with the surge control system of the sister unit next to it. We'll show an example of that in one of the cases later. And we want to assure that the surge control system works for all other station operations. So we want to make sure that it works even if you have reciprocating compressors operating in parallel or series in your station. That might send some pulsations or pulsating flow that could interfere with your surge control system. So all these things we want for a good operation. Now we're just going to walk through a surge control, some of the phases or behaviors of the surge control system or the system itself as we go through a surge event. So I'd like to highlight you, this would be an ESD event or emergency shutdown event. This is kind of an example of the different phases of what happens during that shutdown. So an emergency shutdown involves the compressor speeding down and the process conditions changing while it winds down through its cycle. Again, we've got the head, the pressure ratio on the vertical axis here, and flow along the x-axis here. So what we'll see here is this is an example system for a single cold bypass surge control system. So what we have here is our compressor. The discharge of the compressor sends a high pressure gas through a cooler. And then this is the recycle line. We call it the cold recycle that can be utilized to protect our system from surge when we're in an emergency event. So it's a single cold bypass system. Now what I'll turn your attention to is these little dots here. So we're going to walk through each phase of the surge control event or the ESD event, and I'll get you to look. There's also a little dot over here by the recycle valve, and I'll explain that in just a moment. So the first phase of the system is what we call the pre-stroke delay. So what does that mean? So during the pre-stroke delay, we carry on, we move from the steady state position the emergency shutdown happens. Say we lose power to our compressor, and the speed begins to wind down. Now it winds down along this characteristic impedance line, but there's a certain amount of time lag that happens before the surge control system or the valve actually opens. So we call this the pre-stroke delay. Now that takes time. Well, how much time? Usually it's a couple hundred milliseconds. And that's the time it takes for the surge control system to basically react and send the signal to the recycle valve. So it sends the signal to start opening. Now when we go to phase 2, that's when the valve cracks open and begins to act. Now what you'll notice is there's these two valves, or these two balls we're moving on the screen. As we progress from point 1 to this point here, what's happening is that the recycle valve is cracking open. And what that does is that there's high pressure on this side of the valve and low pressure on this side of the valve. So once the valve opens, the instantaneous pressure at the discharge line side of the valve, it begins to lower. As the valve opens, that low pressure happens, and that actually turns into a pressure wave. And it actually takes time for that pressure wave to propagate back through the discharge system, going in upstream, and get back to the compressor, and to finally unload the compressor. But the compressor actually doesn't see any difference in the pressure until that pressure wave gets there. So I'm just going to click through this once again. We'll see as we go through, that pressure wave reaches the compressor, and finally it arrives, and now the compressor begins to react. And now it's a good thing that pressure wave did that, because that low pressure wave is what rescues the system or the compressor from carrying on down this line, and it rescues it from going into surge. So once that low pressure wave arrives, then the system carries on to phase 3, where the recycle valve is continuing its stroke and opening. And once we get to this point here, the pressure, or the recycle valve is now fully open. It takes time for that valve to open. They're usually very fast, but still it takes time. And once we get to that phase, we head on to phase 4, where the system now is fully open and behaving, and now there's some overshoot that happens. So we'll watch the compressor as it goes through, and it goes through to phase 5, where we have an overshoot, then we have an undershoot, and we follow that overshoot, undershoot continues along this recycle valve resistance line that we're showing here. So that's kind of a quick overview of some of the events that happened in a surge emergency shutdown event. Now, I also want to point out a different situation. You might have a compressor that has a dual system with a cold recycle line like we just had, but also a hot recycle. Now, what's the purpose of the hot recycle? Well, the purpose is for that low pressure wave that we referred to up here to reach the compressor faster. Because right now this low pressure wave, it takes time to go through the cooler, through the piping, and back to the compressor. Now, if we have a hot recycle system, we don't have all that piping to go through, and we can let that pressure wave reach our compressor in a faster way. So I'll just show an example of that. You can see the time difference that it takes for that low pressure wave to reach our compressor and unload it, and allow our protection from surge. So we'll continue on here. Now we'll talk about 5 elements of a well-designed surge control system. The first one is the surge control line. So on a wheel map, we have our surge control line, and that's the first indication of surge, and will allow our surge control system to behave and start working. The control scheme is very important. Recycle valve, as we mentioned, is a very important part. The instrumentation, obviously you have temperature and flow sensors, pressures on the inlet, pressure and temperature on the outlet, and these all feed into the controller that will send the signal to control the anti-surge valve. Now, one other part of the system that's often neglected is the piping system. Now, the design of the piping system can greatly affect into whether your surge control system is a good system and it works, or that it doesn't work like you expected. And so the piping geometry is quite important. So you can see on the outlet there's the cooler geometry. It could be a shell and tube cooler, could be a fin fan aerial kind of cooler. The piping that leads to the recycle valve could be a very long run, short run, bigger diameters, smaller diameters. There's all kinds of design considerations that can happen, especially on the way back to the suction. You might have suction volumes and scrubbers there. So there's all kinds of things in the piping system that can contribute to the effectiveness of your surge control system. And we're going to talk about how those elements are taken into account today and how they're improved with some of these new methods we're going to introduce. So studying the station design piping, we can do that with a full dynamic simulation, and it ensures an optimal surge control system. And the piping system is an enhancement to what OEMs or other people often provide. So we'll carry on here. This will be our first polling question. Do you need a hot recycle system in your facility? So we're just going to pop up a little bubble here. If the participants that are on, if you can start filling in whether you need one or not, just to get a feel for how the participants here feel about hot recycle systems. It's often a very contested and interesting conversations that come out of hot recycle. So we'll just broadcast the results here. We've got quite a few people filling in the poll. I think you should be able to see on your screen now that we've got 60% say maybe, which is a good answer. Some 14% or 14 people say no, and 13 people are saying yes, they do need it in their facility. So that just gives a feel for what we're kind of the questions that come around a hot recycle system. There's a lot of maybes, there's a few yeses, a few no's. So I think we can pass on through this polling question, go to the next slide. So that leads us to some common surge control design questions. First question is, do I need a hot gas bypass system? This is obviously very contested. It costs money to put in. There's a lot of question as whether it's needed, whether it's not needed. There's many strong opinions within the industry. That's a common one, and it's usually a difficult one to solve. One is what is the optimal recycle valve size and type? So if I do have a recycle system, whether it's hot or cold, I need to know what size of valve and the flow through that. What size is optimal? Third question is, how do compressors interact at the station with shared or unshared recycle loops? So if we have multiple units, how do they interact with each other, and can they interfere with each other? If we have reciprocating compressors interacting with our centrifugals, how does that affect us? Can one unit surge another? That's a question we can look at today with one of our case studies. And like I mentioned earlier, will the nearby recip compressors cause premature surge of a centrifugal? And what type of surge analysis is needed? What level do we need? How closely do we look at this? So these are all very common questions, and we're going to be providing some tools today to help answer those. We'll move on here. Some of these new techniques we would like to introduce to you today are different types of surge analysis. So we've got 3 levels. One is level 1. It's a high-level screening using the inertia number. Now this is for to give us a high-level idea of what is our surge sensitivity, what is my system's risk to surge. And that can help us answer some of these questions. Level 2 is, we call it a time limit analysis, for the impedance method. This is a low-cost, quick analysis that we can provide for simple systems to give you a more detailed assessment of the risk of your surge and to give you some pointers, which we'll talk about a little later. We can even help size your valves correctly. And then, of course, level 3 is a full dynamic simulation where we complete a simulation of the piping system with a transient model. And this is really recommended for complex or high-risk systems. So just to go a little deeper in level 2, we'll have a few slides on these. But basically, if this is our wheel map, here's our speed line for our compressor, here's our surge line. The time limit analysis really is a time analysis to see how long will it take for pressure waves in our system to react before to help prevent us from surging. Level 3 analysis, the one we're introducing today, is an alternative to this lumped parameter method. Now, the lumped parameter method is a very common approach in industry today, and really what we're showing today is a real improvement and step change to that lumped parameter method. What the lumped parameter method does is it takes all the piping, all the coolers, all the vessels in the system, and it kind of lumps them into one volume. It really looks at the system from a volume, how long it'll take to dissipate that volume. But it really doesn't consider any of the times of pressure waves bouncing around in the system, and is really inaccurate when it comes to predicting an accurate response of your system. So we're gonna look at those today. In a full dynamic simulation, really it has the wheel map of your compressor, the surge line, the surge control line. It really looks at the full dynamic characteristics. What happens to your compressor even when it surges and goes into full reverse flow? And that's what we're introducing a bit today. So to talk about the level 1 analysis a little closer, it's based on the inertia number. Now the inertia number involves the inertia of your compressor's drivetrain, including the driver. It involves the max operating speed, the mass flow rate, a shutoff of your at the surge event for your compressor, the head at shutoff, and this tau, this time to restore flow. And this is really a time delay in seconds for a valve to open and the pressure wave to return back to the compressor, like we illustrated earlier. So it's quite a basic. It's a dimensionless number that we could calculate, and we've got an exciting offering for you today to offer a free calculator on our website that you can calculate this yourself, which we'll talk about a little later. And so we'll give part of the attending this webinar, you get a free or exclusive link to this calculator, and we'll be illustrating that for you soon. This inertia number really helps us to assess the risk of our system. If you have an inertia number that's less than 30, you have a high risk system, and you might need to consider a dynamic transient or dynamic surge analysis level 3. If you're in this middle area, this gray area between 30 and 100, you have a moderate risk. You might consider looking at a level 2 analysis to kind of understand that risk better. And if you're above 100, you're pretty low risk, although if you don't have much experience with a new type of installation, you may still consider a level 2. This is a real helpful tool to help us give an assessment of the risk in our system. Here's a snapshot, screenshot of our calculator. So we'll be looking through that a little later today. Level 2 is a time limit analysis. We've got some math on the screen here. We're not going to go through it for sake of time, but really it evaluates the time required to restore flow to your compressor suction against the max time allowed. It's dictated by the compressor deceleration and this impedance line. These impedance lines vary or are different for each system based on the piping and your compressor characteristics. And it uses that impedance line to find a maximum time that we can use as far as designing our control system response and have a real hard number that we can design our system to. Level 3 is a full dynamic simulation. And what this does is it solves unsteady gas dynamic equations for the entire piping system. It includes interactions between multiple compressors, and is subject to certain boundary conditions, control protocols, and operational scenarios. So here's some plots here of a dynamic simulation. We've got our wheel map, our surge line, our surge control line. And here, this line here is the zero flow line. Beyond, on the left side of this line, we're into full reverse flow through our compressor. You can see this compressor went through a shutdown event where it was operating here, and then as this sped down through the system, it coasted down quite nicely and did not surge. Here's an example of some compressors going into surge, which we'll look at later in one of our case studies. Here's some of the equations that we use in the level 3 analysis. It's a very complex analysis. We have the continuity equation, momentum equation, energy equation. And all these are partial differentials. We won't go through the math in this. There's lots of papers we can refer you to if you're interested in these methods. We use the method of characteristics to solve all these hyperbolic partial differential equations. And the method of characteristics is quite well known as a solving tool. It's quite computer intensive and calculation intensive, but we aren't going to go through much of that today. The main driving force of this analysis is the compressor dynamic equation, where we have the mass or the work of the driver. It includes the inertia of the driver, the speed of the driver, the change of speed over time. It also includes the inertia of the compressor, the speed of the compressor, the change in speed of the compressor over time. It also has the mass flow, head, and efficiencies and windage losses. The surge is really dictated for an ESD or a fast stop event, which is really the most severe kind of case that can send your compressor into surge. It's dictated by the timing of the gas pressure forces overtaking energy imparted by the rotating impeller. The result is a system instability, and these system equations are used to really predict accurately what's going on in your system during a surge event. Spatial effects are important. So as we mentioned before, small time steps occur which allow these pressure waves to propagate through our piping system and really affect the timing. They become very important during a fast transient event like an ESD. Mentioned earlier, two broad approaches are available in the industry. The full spatial and temporal dynamics approach, which is what we're talking about today, is what Beta offers, and we use a software called Centran. This should actually say number 2, but the common lump parameter approach, and this is very common within the industry. Most people have access to this type of analysis. It only it talks about the lumped volumes within the system. It doesn't go through the spatial time steps like we're talking about. So it really does compromise the simulation accuracy. So I think what I'll do now is I'll hand it over to Mary Beth, and she'll walk us through our first case study.
Thanks, Jordan. Hopefully everyone can hear me okay. I think I might have been the cause of the echo earlier. Thanks to all the attendees also for calling into the webinar and participating. Just a reminder, you can submit questions at any time throughout the seminar, so feel free to go ahead and submit those and we can queue them up for the end. So for the second half of this webinar, we'd like to highlight 2 case studies. Both of these case studies were conducted recently by us, and they were good examples of why a level 3 analysis is often necessary, and really can't, some of the issues can't be seen in any other type of analysis. And this is often necessary for high-risk systems with a high sensitivity to surge. So in our first case study, we have 2 compressors that are operating in parallel at an existing facility, and a third compressor was added, a third centrifugal, also in parallel to accommodate more flow. So on paper and from a first glance, it was a well-designed system because each compressor had its own dedicated hot gas recycle loop, in addition to a cold recycle, which was also independent for each compressor. But they did share a common suction piping header, and they both, or all 3 of them, obviously fed into a common discharge pipeline. And on top of that, the hot recycle valves were oversized to meet the flow and time specifications with an equal percentage valve. So we can see the picture here of the station. Unit 6 and 7 at the station are here in this back house, and they were existing, and the operating company chose to add the third compressor, which was also operating in parallel over on this side of the compressor station. The suction gas comes in here at the bottom, and discharge lines leave the station over by Unit 6 and 7. And it is interesting to note that this station also had a number of reciprocating compressors also operating in parallel. So this is a nice schematic that clearly shows exactly what's going on with the surge control systems. You can see each of the compressors have their own hot recycle system with hot gas recycle valve and a downstream check valve that is meant to accommodate the ESD event. So the check valve would close and the hot gas recycle valve would open in the event of any one unit's ESD, and all of them would act together if the whole station was ESD'd. And the suction gas comes in to the station down here through a suction scrubber, and they actually added a second suction scrubber dedicated for Unit 8 with the addition of the new flow. And then the cold gas recycle loops run through the cooler. Each unit has its own cold gas recycle and then a cold gas recycle valve as well for each unit. And these are the downstream check valves for those cold recycle loops. So our first step in any surge study is to go ahead and calculate the surge sensitivity or inertia number. This is again implemented on our website as a free calculation tool. And you can see here that the inertia number for all three of these units was relatively low. This is usually brought on by having a low inertia for the entire drivetrain and a high head and flow combination. So the non-dimensional inertia number ended up being below 30, which usually points you towards doing level 3 full dynamic simulation. And that's what we did in this case. So the first couple plots here are going to show you the simulation results on a performance map. And the y-axis, again, is your isentropic head. And the x-axis, even though you can't see it here, but it's actual inlet flow. So it's your suction flow rate. For this first scenario, we're looking at the event when all three units are ESD'd for the entire station. And you can see what happens is that the surge control system acts very well to protect the units from surge. They are basically operating at a high flow, relatively close to probably 100% of its speed on this line for both Unit 6 and 7. You can see that here, sorry. And then they move towards the surge control line, which is indicated by this dotted line. The surge control system kicks in, knows to open the recycle valve, and moves it just in time away from the surge line, restoring sufficient flow to the inlet of the compressor, and basically kind of overcorrects in both Unit 6 and 7 and Unit 8's case. But it basically brings the compressor down in speed safely and avoids the entire surge region of the compressors. So this is acting really well, and we were pleased to see this in the simulation. However, scenario 2 here is going to show the event when Unit 8 is fast stopped. This is the new unit that they added, and either fast stopped or ESD'd, but we want to keep Unit 6 and 7 running at the station to keep the entire compressor station online. So in this event, we see Unit 8, its surge control path, it's basically coming down in speed because the ESD button was hit, and the surge control system is acting to protect Unit 8, and that works just fine. But at the same time that this happens, Unit 6 and 7 are supposed to stay online and be relatively unaffected by Unit 8. But as you can see by these surge cycles over here, and crossing this y-axis here basically indicates reversal of flow, negative flow for the suction side of the compressor. And so Unit 6 and 7 go into a full-on surge cycle that's kind of repeated. Because they're not coming down in speed, the surge cycle happens at close to full speed, which can be damaging for both compressor units. So the question was, why did this happen? And the answer is it's actually in the station dynamics that you have to see and look a little bit closer through the full dynamic simulation. So these are our time trace plots. This is our transient response that we're able to get out of our full dynamic simulation, level 3, for pressure, suction and discharge, temperature, suction and discharge, the compressor speed rundown behavior for Unit 8 when it's ESD'd, and then the mass flow rates at different points in the system. So the red line here shows our mass flow at the compressor inlet. The green line shows the mass flow through the check valve in the recommended design, and the blue is our recycle flow, so the flow through the recycle valve. And because Unit 8 didn't surge, we can see that the recycle valve quickly opens to full on and has high mass flow through it, and keeps the red line here as the compressor mass flow positive throughout the entire compressor rundown. Sorry. So that's shown here in the transient response. However, if we look at those same plots for Unit 6 and 7, this is Unit 6 with the pressure, temperature, mass flow, and compressor speed. Again, the bottom left plot showing the mass flow rate, you can see that same surge cycle that happened in our previous performance map for Unit 6. So while Unit 8 was ESD'd and brought down safely, Unit 6 underwent a number of surge cycles, each lasting for about 1 minute or 1 second in duration, and it happened 3 times in this transient response. So we definitely had a problem, and what ended up happening was the overall flow in the suction header was basically being stolen by Unit 8, and Unit 8's ESD event caused the high hot gas recycle valve and the cold recycle valve to open when it ESD'd. And both of those valves opening at the same time resulted in a huge amount of flow going back to Unit 8, and there simply wasn't enough gas pressure and gas flow in the suction header for Unit 6, and that's where we ended up getting this reversal of flow and surge cycle for both Unit 6 and Unit 7. So in conclusion, the individual independent recycle loops were adequate, and the hot and cold recycle valves were adequate in protecting the individual units from surging. But when we looked at the overall station dynamics, in the event that Unit 8 ESD'd or fast stopped, both Units 6 and 7 underwent surge because of that high flow dump from the cold and hot recycle loops of Unit 8. And so the unit recycle valves being oversized and that common suction header system basically led to this event where Unit 8 was stealing all the other flow from the other units in the fast stop event. And to basically solve this problem, we had to isolate the independent loops and slow down that cold recycle valve from opening. And basically that added some delay and helped to isolate the individual units and keep Unit 6 and 7 from surging when Unit 8 was ESD'd. This case study definitely highlights the need to take a big picture view and look at the overall station dynamics, how one unit ESD'd and its surge control system can affect the other units when they shared that common suction piping header. So it's one of those things that the level 3 analysis can definitely analyze for you. So before we jump into case study 2, we'd like to take a moment to do one more polling question, and this kind of leads into case study 2. That's, do you think check valves, hot gas check valves, are required on the discharge of your compressor? So this is the check valve that goes basically downstream of your takeoff line for your hot gas recycle valve. And the question is, do you prefer to use those? And it looks like, if everyone can see the results, we have a good large majority, about 75%, saying yes, definitely check valves are necessary on the hot gas recycle line. And that's the kind of result we wanted. We also have about, 18% saying it depends. So we'll go ahead and go into the next case study that relates to check valves. So for case study 2, we have a little bit more complicated system. In this installation, a facility was being upgraded, and we were adding 3 new centrifugal compressors. The operators also chose to use electric motor drive and drive the compressors at a constant speed, but they added torque converters so that they were able to get that variable speed capability for process control and good operation of the compressors, even though the electric motors continued to operate at constant speed. So they avoided the need for a VFD here. And the units were able to operate in multiple configurations, which also led to a more complex system. They had the capability to operate all 3 of these in parallel, or two of them in parallel, feeding a third in series, or 1-in-1 series operation. And in this design, they implemented individual hot gas recycle systems with dedicated hot gas recycle valves, but there was no check valve put in on the hot gas recycle system. They did have a downstream check valve downstream of the cooler, but they didn't have that intermediate check valve, and that was done mainly to save cost, but they compensated. So they came back in and said, well, if we size the hot gas recycle valve to be greater than normal and include that additional flow volume that we need to relieve through the cooler because we don't have that check valve in place, perhaps this would be an adequate protection. So this is a kind of complicated piping layout, but I'll walk you through it here. Let's see if I can find my pointer. So this is our compressor here, and our blue line indicates the inlet suction line. The orange is the discharge line leaving the compressor. And this is the takeoff for the hot gas recycle system here and the hot recycle valve. So in the event of an ESD, this recycle valve would open and the flow would run through this hot gas recycle back to the inlet of the compressor in adequate time for the surge control system that's needed to respond to avoid surge. The cold recycle line is shown here, and that's basically another way to get flow back to the compressor after the flows run through all of this cooler piping. And again, the check valve was put downstream of this entire cooler piping. And we didn't have the check valve for the hot recycle system, which would have normally been placed in this line here to isolate all of that additional downstream cooler volume in the event that the hot recycle valve needed to open. So again, the first step that we did in this analysis was to run the surge sensitivity number, and you can see that both of these, all three units, had a low inertia number. Number lower than 30 usually means to run the full dynamic simulation. So that's a high risk, high surge sensitivity. And we did a number of cases, but the one I want to focus on is all three units in parallel operating relatively close to the surge control line. And that's the dotted line shown here and this operating point. So without the downstream check valve in place, we basically can look at our transient responses from the full dynamic simulation. Again, we have pressure, temperature, compressor rundown, and speed over a 10-second period. But down here, our mass flow rate is an interesting one to look at. And that's because our red line, again, is our compressor flow. And you can see how it dips down for a full 4-second period. So this is a 4-second reversal of flow, 4-second surge cycle, enough to cause considerable damage to the machine. In the same time, the recycle valve quickly opened and was showing positive flow through the recycle system. But you can see that even though it quickly opened, for about a second, there was positive flow at the compressor, but then it kind of went into this late surge cycle, basically because the recycle valve was overwhelmed by that downstream volume. And in this plot on the performance map, again, you can see that same late surge cycle where the compressor was initially protected, running down in its speed, and the recycle valve was open, but then the recycle valve was simply overwhelmed by all the discharge volume and went into the surge cycle on all three machines in the simulation. So we came back in and said, well, what about going ahead and adding the hot check valve right here in the basically downstream of where the hot recycle valve takes off? And if we could protect the machines better by adding that, let's run the simulation again to see what happens. So here's these same response plots, but with the addition of that downstream check valve. And you can probably see that best in this lower plot on the left. The downstream check valve now is the green line, and it's sufficiently closed, so we don't have any flow going through that piping, and we've isolated the cooler gas volume that's downstream of it. The recycle valve acts in much the same way, but in this case, without that added volume, the compressor maintains positive flow as it runs down in its speed. So the surge control system acts as it should and protects the compressor. And you can see the 6 cycles here where we've got much better behavior where the recycle valve's opening, we're staying positive, and we're coming down in speed without going into surge. So finally, this case study 2 wrapped up by showing we definitely had an extreme need for a downstream check valve. And oversizing the recycle valve, even though it guaranteed enough response time and opened quickly enough, it simply wasn't adequate to relieve all of that downstream pressure. But with the addition of the downstream check valve, the hot gas bypass valve was undersized and relieved the full system volume capacity. And that's without the downstream check valve. So when we added that check valve, we basically had a correctly sized system, and we didn't have surge. And it's interesting to note that the potential cost savings here of the larger recycle valve and the system without a check valve were outweighed by the lack of surge protection when you didn't have that check valve in place. So by saving money to omit the check valve, they basically caused additional surge risk for their machine. This is another instance when the level 3 analysis uncovered that system instability and the lack of protection because we were able to simulate all of the different flow points in the machine and the overall piping system. And if we have time, I'd like to really quickly demonstrate our new surge sensitivity calculator on the Beta website. So I'll go on to our Beta website homepage. And if you can all see that, this is our basically surge sensitivity calculator that we'll be giving you as part of this webinar. And it's linked off of our homepage, and it'll be under our Knowledge Center under Tools. And with this surge sensitivity calculator, it's fairly simple for the user to come in and enter a couple of the main key parameters. And that includes rotor maximum speed, your maximum head at surge in kilojoules per kilogram, a maximum mass flow at surge, and this comes straight from your performance map given to you by your OEM, the number of wheels on the drive train, and then the type of drive. This is extremely important for calculating the inertia of your overall drivetrain. So we have aeroderivative gas turbine, a frame unit, or a motor-driven gas turbine. And so in this case, I chose aeroderivative gas turbine drive. We'll put our piping length and the recycle loop and a speed of sound that works for the natural gas mixture or whatever gas that you're running. We have some basic speed of sounds here over at the right, but you can obviously enter that from your equation of state calculator. And then when you hit submit, it comes in and calculates an inertia value for you. You can also input that inertia value. And then the key number here at the bottom is the inertia number. So that's the non-dimensional number that we were talking about before. And in this case, it's calculated a number of 23. Any number of less than 30 is a high risk. So this is available for all participants in the webinar, and it's a free calculation tool that'll help guide you towards what additional surge analysis you might need. So going back into our presentation, I think this wraps up my portion, and I can direct it back over to Jordan.
Yeah, thanks, Mary Beth. So that's really great, and thanks for going through all that. Just to give you a quick summary before we get into questions of the offering. So this level 1 surge sensitivity calculator, that's free. It's going to be available exclusively to the webinar participants today for a period of time before we release it to the general public. And it'll give you an overall risk calculation of your installation to surge. A lower number obviously suggests higher risk. High inertia number suggests lower risk. So that's really there to help industry kind of answer some of these crucial questions about do I need hot gas recycle and whatnot. Level 2 goes a step further, where we can really dig into how what size of valves and what is your real risk. It's a more accurate calculation of a risk. This is something that can be done, usually in under a week with the right information. Some outputs of it are you get an optimal valve size for your recycle lines, whether it's cold or hot recycles. It specifies the necessary valve response time, which is a real key parameter that you can send on to your vendors. It gives a better assessment of the risk. It also gives the opportunity for a qualitative assessment of the risk too. So there's a lot of experience that we have, and given a certain system layout, we can add some of that experience and to the risk as well. And it's, like I said, it's fast, and we can often turn it around in less than a week. So it's quite an affordable and fast study that we can get through. Again, often level 3 is the most accurate assessment of real surge behavior. And it models actual piping layout, valves, and components. It identifies dangerous operating scenarios, recommends detailed design improvements. It's the most comprehensive assessment of surge. And the neat thing about it is often compressors, these stations and units are being designed with more variability and flexibility in their operation. So it really allows the opportunity ahead of time to evaluate how your system will respond given the different scenarios, whether there has parallel, whether it's operating in series, whether it's operating closed and different operating states. You can really test the effectiveness of your surge control system in each of those. So to keep going here, that'll bring us into the question period. There's a lot of great questions that have been submitted. Thank you to everyone. We've got about 5 minutes to get into some of them. I don't think we'll be able to get into all of them. I just wanted to there's some quick ones I think we can get out of the way here. We look from Kajitan. I'm going to submit that out. Kajitan asks, how is the margin screening number for the inertia number, I'm assuming 30, chosen? Is that an empirical or a theoretical value? Basically, the criteria that we have with the inertia number is based on empirical simulations done on real systems that are out there. So that was we submitted a paper to the Turbo Machinery show last year, and in that paper we've got 25 different units and different compressor installations where we did both the dynamic study and did all these calculations, and we could really calculate the risk and understand the risk. And the inertia number is based on those real units out there. So that's a quick question to get out of the way. Another one here. Tom Bailey. We'll put that out there. How do you model the response of the recycle loop? Are you assuming that for your level 3 analysis that one or both recycle valves are open? And how do you determine how long it takes for the valve to open? So that's a really good question. And the answer is quite simple. We know the valve timing that they have open because one, the valve OEM can specify the opening time, and two, we know the trim characteristics of that valve, whether it's an equal percentage valve, a Copen valve, a linear type valve. And so what we do is we don't assume, we actually model by millisecond what is the opening state of that valve as it opens based on the manufacturer specifications. And we can validate these too, because before they ship these valves, often the manufacturer will do a shop test, and so you can see the real shop test data as well. So that the valve behavior isn't assumed; it's actually modeled time step by time step. How open is it versus time? I hope that answers your question, Tom. Another question here from Adrian, and this is one that's come up by a few people. I'll post it out here. So how do you predict the compressor performance off the map? So the surge cycle. So what happens when it goes past the surge line and goes into negative flow? When operation in that region has not been verified by manufacturers. So that's a really good question. And we have some references in the paper we submitted to the Turbo Machinery conference last year. And really it goes back to a particular MIT professor or researcher who did some empirical testing on this phenomenon. And he did empirical tests that determined there's a relationship that can be followed, a cubic type function, that can be used to accurately predict what the compressor's behavior will be when you cross that surge line into the negative flow regions. And so there's a lot of papers we can refer you to research that. It's quite a technical question, but we can, if you contact us later, we can refer you to some of those references and you can look at them yourself, Adrian. So thank you so much for that question. We can get into another question here. Maybe Mary Beth, you can take this one. This one's from Tufik. What type of recommendations come out of the study? And should the study be followed up with a field check? Mary Beth, you want to handle that one?
Yeah, I think that's a really good question as well. I mean, it definitely depends on what's being analyzed in terms of the number of units at the station and what's already been done by, say, an EPC or an OEM. So, I mean, for kind of a blank sheet type analysis, we could come in, recommend exactly the type of recycle valve and the relative lengths of piping that we'd like to see used for the recycle lines on the cold and hot recycle. For something that's already been basically designed, we would be checking the recycle valve response time and the overall response of the system, in addition to the dynamics with other units. So it kind of depends on what the user's already done and, you know, what stage they're in. And yes, a field check's always nice, but we don't want to surge your unit during a field study. So.
Yeah, so I think that's a good point. And some of the other recommendations could be piping changes, location changes, valve changes, and so there's quite a lot that can be done. So we're running out of time here. We've only got a few seconds left. One question that's been coming up is, can we have a copy of the slides after? And what we'll be doing is we will be posting a copy, a recording of this webinar later on from the website. So we'll be sending the link out to everyone so you can refer to this webinar once again at a later date. And maybe we can close if we can hold you up for another minute. We've got a good question here from David Rogers. How closely did your simulations in these case studies mirror actual recorded data? That's a really good question. And David, what I'll do is refer you to our website. There's our centrifugal compressor pages. And we have some really good plots of data where we've run our simulations on a real compressor system while actually really measuring the flow and disturbances in the system. So we have some really good plot that we can send you that shows this level 3 transient model and how well it predicts with real flow and pressure data. So we can point you to that. In fact, maybe in a mail out after the webinar, we can point you specifically to some information on that. So I think that's it. There's a lot of other good questions here. We don't have time to get through them all today. What I'd recommend is for any participants who still have questions they want to ask, please send Mary Beth and myself those questions. We can talk about them in person or together and answer any questions you might have. We refer you also to our website. We've got a lot of good, if you scroll down through the pages, there's a lot of good resource material, papers, and different case studies that you can access. And also at the end of today, when we send out the follow-up, we'll give you the website link to the free calculator. Excuse me. And then also we're going to have a PDF of one of the case studies, case study 1, kind of a PDF document. You can go through it yourself and in a little more detail with as much time as you need. So I think that's enough to wrap up our webinar today. We really appreciate everyone attending. Lots of good questions here. I hope we can answer some of these for you. Feel free to contact us, and we look to give you more information on this important topic in the future.